Assalamualaikum and hello everyone. We are from Group 22. I am Nur Anis Mastura. Together with me, my group members, Ainur Ashikin, Muhammad Nabil Imran, and Muhammad Shakir Shahzwan. Today, we'll be presenting our study on CFD simulation of a microchannel heatsink, focusing on how we can enhance the thermal management in electronic cooling through optimized channel geometry. As electronic devices become smaller and more powerful, they generate increased amount of heat in compact spaces. Without proper thermal management, this heat can lead to reduced performance, shortened component lifespan, or even system failure. Okay, let's take a closer look at the problem. Firstly, high heat generation in modern electronics require strong cooling solution. Secondly, the traditional air-cooled heatsinks often fail to meet the demands of high-performance systems. This brings us to microchannel heatsinks, which are much more efficient due to their higher surface area and compact size. However, they come with design challenges such as increased pressure drop and uneven fluid distribution. Most importantly, the geometry of the microchannel, whether it's rectangular or trapezoidal, they play a key role in both heat transfer efficiency and also fluid flow behavior. To address these challenges, our study is focused on two main objectives. Firstly is to model and simulate microchannel heatsinks with different channel geometries, including rectangular and also trapezoidal, using computational fluid dynamics (CFD) tools. Secondly is to identify the optimal geometry that provides the best thermal performance by maximizing heat transfer while also minimizing pressure loss.
Assalamualaikum, my name is Muhammad Nabil Imran. So for the geometry, we have three models. The first model is trapezoidal, and the second one is rectangular, and the last one is circular. For the mesh and initial condition, we have three domains. The first one is inner domain, the second one is hot domain, and the third one is cold domain. And the initial condition of hot inlet for temperature is 70 degrees Celsius, and for velocity is 0.5 meter per second. And the next one going on, we have the initial condition of hot outlet, which is counted at the pressure gauge, and it's 0 Pascal. And the next one is for the cold inlet, the initial condition, and it's for the temperature, and it's 20 degrees Celsius. And the last one is for velocity, it's 0.7 meter per second. So here we have the result of our CFD simulation. So we have compared three models that we have used, which is the trapezoidal, rectangular, and circular. So we have compared three things, which is the pressure drop, heat transfer rate, and performance index. For the pressure drop for our first model, it is 117.30, and the heat transfer is 371.98, and the performance index is 3.17. So the second model that we have used is the rectangular channel. The pressure drop is 0.4792, and the heat transfer rate is 1728.24, and the performance index is 3606.51. And the last one and the third one also, we have the circular channel. We have the pressure drop at 0.0869, and the heat transfer rate at 1036.25, and the performance index is 11924.63. And as you can see, we have two examples of the temperature control and pressure control for the trapezoidal channel.
Next, we are going to see the possible of errors in our project. So number one is mesh quality and resolution. One of the most critical source of error in CFD is the quality of the mesh. As we know, if the mesh is too coarse or uneven, it can produce inaccurate predictions of heat transfer and fluid flow, particularly in microchannel simulations where boundary layers are thin. To reduce this error, we perform a mesh independent study, but limitation may still remain depending on the refinement level. And next, our error is the simplified geometry. The geometry used in our CFD model is idealized. In practice, microchannels may have rough surface, manufacturing defects, or rounded corners, all of which affect fluid flow and heat transfer. Our COD models assume perfectly smooth and symmetric channels, which do not fully capture these real-world complexities. So this simplification might lead to underestimation of pressure drop or overestimation of heat transfer efficiency in the actual application. And our last error is boundary condition assumption. Another important source of error comes from the assumption made in boundary conditions. So for example, if we applied a constant velocity and temperature at the inlet and defined adiabatic walls for the sides of the microchannel, while these assumptions help simplify the simulations, they do not always reflect real-world scenarios where temperature or flow rates may fluctuate and heat can leak to the surroundings. So these idealized conditions may affect the accuracy of the predicted pressure, drops, and also temperature profiles.
So, Assalamualaikum and a very good day. My name is Ainur Ashkin binti Abdul Sharma. My metric number is A193448. And now I will explain about our analysis and conclusion. So I will begin with analysis. Okay, so from our simulation result, the rectangular microchannel gave the best performance overall. It removed heat efficiently and didn't require too much pressure to push the fluid through. That means it's both strong in cooling and efficient in energy use. The circular channel had very low pressure drop, which is good, but it wasn't as strong in heat transfer. And lastly, the trapezoidal channel helped mix the fluid well, but caused a lot of pressure loss, which isn't ideal for saving energy. So when we look at the factors, which is cooling, flow, and energy use, the rectangular shape was the most balanced and reliable option. Okay, so in conclusion, this project showed how important channel design is in cooling system. We use CFD to test everything virtually, which help us find the best design without building real parts. This kind of simulation can really help engineers build better cooling system for future technologies. So that's all from our team. Thank you so much.